Welcome everybody for on this today's webinar on high performance computing. I have to say I'm happy that you have joined us today. So without any introduction, let's go to our agenda today. In short, this webinar will be theoretical and conceptual. So I will address it from a perspective of a user, of a researcher, and I will try to cover different component of a hardware. I would try to cover what I believe a user, a researcher should know about high performance computing. So I will try to bring you a little bit closer to how HPC system look like, and cover different component hardware and software of this kind of system. So it will be a high level description. It goes from architecture of a compute node to CPU, GPU, and network fabric architecture, communication framework architecture, also briefly about the file system architecture. And then if I have a little bit of time, I will shortly talk about some optimization strategy using some new features. So this is the agenda of this webinar. And before we dive into the details, so let's take a look where we stand in the world of supercomputing. So I list here the top 4 supercomputers as of November 2024, and El Capitan is the powerful, it seems, the powerful supercomputer so far, with about 11 million cores, more than 11 million cores. So this cores is actually a mix between CPU cores and the GPU cores, and delivers a performance of more than 1,700 petaflops. That's about exaflops, is billion of flops. So the building this system has cost about more than 600 million. So it seems it's a good business. And the purpose behind building supercomputer is to advance nuclear weapon science and scientific discovery. So talking about scientific discovery, this is an interesting study that has been done very recently. So so this is in the context of drug design. So where where researchers they combine advanced AI techniques with the large database, up to 40 billion molecule screened against the SARS-CoV, and more importantly is really the computational power. So without computational power, this study wouldn't barely be possible in conventional and traditional systems. So the simulation in this study took about 90 days on 250 GPUs, and only 1 day on 27,000 GPU on the supercomputer Summit. So I think this study would have taken less than a half day if it was done on the supercomputer El Capitan. So this is a simple examples that shows the power of supercomputing. So of course now the question is, why should we care about the hardware architecture? Well, I think there are many reasons that we should care about understanding the architecture of HPC system. So one of the reasons is performance optimization. So HPC system basically relies on parallel processing, meaning that understanding the architecture, it helps users to optimize their code for a better performance. But not only that, it helps users take full advantage of the system by utilizing some new features, and they are fast development in the hardware technology, and is a good practice to be able to fully utilize the capacity of a system. But also caring about HPC system is about optimizing the resource utilization. And there are actually groups who are using about 100 million CPU hours per year, and that is about 10 million krona per year. And sometimes 50% of the resources are wasted from different reasons. So Optimal use of resources reduce computational time at also cost. But also when things go wrong, understanding the architecture of the system, it helps to have a reasonable diagnosis of issues. I think another important, probably just been curious about how HPC architectures look like. And one of the questions I personally get often asked is, when you have such a system with thousands of servers, how all these servers get connected to each other such that each server can talk to other thousands of servers. And last, I think is also a joy to understand how things work. Probably that's most important aspect of answering the question. So let's take a look at the history of supercomputing. I highlight here some important period in the last 70 years of computing, starting in 1961, where the first machine that delivers computing at the level of megaflops, million operations per second. So actually, it took 40 years before the emergence of the area of high-performance computing in 2004, and that's due to the development of in the context of genes in biology. And only 4 years later, in 2008, was the first supercomputer that operates at the petaflops was introduced. That million of a billion of operations per second. So, and a few years later, in 2012, the performance increased by a factor of 16. So, and now today we are in exascale computing where the performance is in the level of a billion operation per second. So so here I basically use some terminology. I think it's good to define some terminology before we dive into more details. So how we define a heterogeneous system. So this is a heterogeneous system is a system that can be composed of different hardware and software. So it can be CPU and some integrated with some GPU accelerator. And the purpose behind integrating GPU accelerator is to increase the performance and the scalability. But also it's important to clarify the difference between clusters and HPC cluster and supercomputers. So a traditional cluster is simply a collection of computers that are just connected in traditional way. And the server simply is unconnected node or unconnected compute node. A HPC system, however, is a collection of compute nodes, but they are all connected via a high-speed interconnect. It's a high-speed network. By doing that, we form a single system. And here we can distinguish between HPC cluster, but also supercomputer. We can we can make a difference based on the range of the peak performance operation. An HPC cluster, basically they operate in the teraflops until petaflops, meaning that from million of billion operation to million of billion operation per second. While the supercomputer, they are in the range that goes from petaflops to exaflops. So talking about flops, let's see how we define flops. So flops is a quantity that helps measure the performance of a processor. So it's the abbreviation of floating point of operation per second. And the theoretical peak, the way it's measured is based on this theoretical peak performance. So you can see that the flops is proportional to the number of cores. So here we have the flops. So we have to distinguish between flops with the big S and flops with the small x. Flops with the small s is a way of encoding numbers. For real numbers, we have 64-bit. Simple precision, we have 32-bit, and so on. So just to give you an idea about the meaning of flops, if we have a machine that delivers an performance of 1 gigaflops. That's equivalent of process handling billion floating point operation every second. For matching is equivalent to performing one calculation every second for almost 32 years. So in the same way, we can define teraflops is it's million of a million calculation per second, and petaflops million of billion calculation per second. And then we have exaflops, and that's billion of billion calculation per second. And it's interesting to know that 40 years ago, the first supercomputer that delivered an operation on gigaflops. So after 40 years, the performance, interesting to see that the performance has increased by a factor of billion. So it shows the power of supercomputing. So talking about flops, intuitively one can say that if the flops here, if going from 64-bit to 32-bit, the performance or the peak performance can increase according to the type of the number. Theoretically, it seems theoretically that's what the formula shows, but in real life is not always the case. For instance, if you look at the performance that carried on 64-bit, one can expect that the performance that it should be twice performance for 32-bit. This is not the case here, but for 16-bit, we can see that the performance has increased by a factor of 4. So this shows that there is something that goes beyond the hardware, that affects the performance of an application, which is obviously either the software stack that is not well optimized for the system, or obviously that the user's application that requires more optimization. So let's dive now into the hardware architecture, and let's start looking at the basic of cluster architecture. This is the basic architecture of a cluster. So in general, the way it works is that you have a user that try to interact with the login node via a secure shell SSH connection, for instance. The user submit a job which is taken care by a scheduler. It can be a Slurm, for instance, and the Slurm decides where and when the job should be submitted, should be performed on each compute node. And here we have a grid of compute nodes. So each compute node, if we have an heterogeneous system, so each compute node will be attached is a combination of CPU and GPU, but also there can be some local disks. And all these compute nodes, they are interconnected via a high-speed network. That's the case in an HPC system. So in addition to that, we have some storage system that is attached to the cluster. So this is the basic architecture that we have so far. And in this webinar, we will try to zoom in on different components of this cluster and try to provide some insight into the role of each component. So let's start by compute node. This is a picture of a compute node. The compute node consists of 4 NUMA nodes, NUMA 0 to NUMA 3. So each NUMA node consists of 18 threads, such that 16 threads. So each 8 threads, they share L3 cache memory. So this is really interesting in terms of optimization, because accessing the L cache memory is faster than accessing the main memory. And understanding the architecture of the compute node, it helps optimizing the application by adding very simple options. For instance, CPU affinity, which means that you specify the closest GPU to the NUMA node. Let me give you an example here. The NUMA node the NUMA node 0, for instance, is connected to the GPU 5 and the GPU 4. So meaning that if the application is using CPU 0, CPU 07 and CPU 15, and the communication between GPU and GPU 5 taking place, it will be the communication. It will be 4 times faster than communicating between the GPU 5 and the GPU 7. This is true when you have a large set of data. Basically, you wouldn't be able to notice any communication improvement if you have a small set of data. So this is one of the interesting things about understanding the architecture. So this is about the CPU infinity. So back to the compute node. So each compute node can be connected to a local storage. So this is not a general behavior. Some systems do not have local storage, do not have temporary storage. And what happened is that the temporary storage can reside in the main memory. So this is something that user need to verify. And sometimes what happened is by using a large temporary memory, temporary storage, the application can run out of memory. So on the other side here, we have, as I mentioned, each NUMA node is connected to a GPU, but also we have a network interface cards. That's marks the ending point of a compute node from which the compute node can connect to other compute nodes. So and next we will try to dive into a single CPU and a single GPU and get some insight into the architecture. So this is the latest CPU processors by AMD. The CPU process consists, this is a new architecture. It's very different than the traditional architecture that we are used to. The architecture here consists of you have 12 CPU die. We have 12 CPU die. So each die consists of 16 cores, and all these cores, they share L3 cache memory of 32 megabytes. And of course, each core has its private L2 cache memory of 1 megabyte of capacity. So this is very important. Understanding the memory hierarchy of a system is also very important in terms of optimization. As we know that accessing the cache memory is faster than accessing the main memory, meaning that if an application is well optimized to make use of L-cache memory, it will improve the communication, and it will reduce the communication latency. So this process comes with 6 terabytes of memory and with 614 giga the bandwidth per second. And the core density of this process is up to 192 cores. This is apparently the highest CPU density available today. So I suppose with this kind of CPU processors, you can really run some AI trading and do some relatively okay simulations. So this is for the CPU process. This is an overview of the CPU process architecture. Let's look at now the GPU part. I'm listing here the well-known GPU vendors, so NVIDIA and AMD. So this is the latest NVIDIA GPU Blackwell and the latest AMD GPU MI325X. Here's some specification about each GPU, and for reference, I take the latest AMD CPU as a reference just to have a comparative between this GPU and the CPU. So the NVIDIA GPU comes with 192 streaming multiprocessors. For AMD, the equivalent is compute unit, 304 compute units. The NVIDIA GPU, the Blackwell, consists of more than 24,000 CUDA core, while AMD 325 of roughly 20,000 core or stream processors. Built in, this GPU comes with 92 billion transistors. There are more transistors on AMD than on NVIDIA. On the other hand, on the CPU, we have only 12 CPU dies and 192 cores. So that's, and in terms of the bandwidth, 8 terabyte of bandwidth, 6 terabyte of bandwidth AMD, and only 614 gigabyte of per second. So this is, it shows that the GPU, they are built for high throughput, but also for low latency. And there is some particularity between GPU and the CPU. While the CPU, a CPU can run multiple processes on the CPU simultaneously, but that's not the case with the GPU. The GPU are designed for multiple threads, mostly using the concept of single instructions on multiple data. This means threads, they operate on different sets of data in parallel, using the same instructions. So this is just to promote Norway's next supercomputer, Olivia, and in our system we will basically use the NVIDIA Grace Hopper super chip. And because we are going to use this, I think it would be good to give an overview how the architecture of this of the NVIDIA Grace Hopper super chip looks like. So this is the architecture. From this architecture, we see that the super chip consists of CPU and the GPU. The CPU Grace consists of about 72 cores, and it has up to 480 gigabytes of memory, and the bandwidth is about up to 500 gigabytes per second. The CPU is connected to the GPU via NVLink with 900 bandwidth. The bandwidth of 900 gigabytes per second is a bidirectional bandwidth, meaning that 450 on each direction. So on the other hand, we have the GPU Hopper. The GPU Hopper comes with a memory up to 144 gigabytes and a bandwidth of up to 4.9 terabytes per second. So the GPU comes with the ability of connecting with multiple GPU system and up to 256 GPU. So this is an interesting architecture of the super chip, where the CPU with ARM architecture is connected to Hopper GPU. I think with such a powerful super chip, what is needed now is basically good scientific application that take advantage of this kind of systems. So before I go to the
would you like to take one question now?
Yeah, before I go to the next part, the question is a core the same as transistor? No, but the building block, of course, is transistors, meaning that the more transistor you put, the more you can create more cores. Let me see if we have more questions before I go to the second. Okay, I think that's the only question we have, right?
Yes, that's the only one.
Yeah, let's now dive a little bit to the architecture of the network fabric. I want to go back to this picture just to mention. I have mentioned the network interface cards, which are the endpoint of each compute node. This is the point where a compute node can connect to another compute node. So let's talk a little bit about network interface card. Network interface card is provide a physical interface between compute node and the computer network. To understand it much better, let's look at this scenario here, where we have two compute nodes, each consists of two GPU. Each GPU is attached or connected to a network interface card. So the idea here is when a local process starts to send data from node 0 to a node 1, it uses the network interface card, and via the high-speed network, it goes through the network card or another compute node, and from there to the compute nodes. So the role of the network cards is to communicate, to enable communication between different compute nodes, and also has a role of enabling what we call RDMA protocol, remote direct memory access. RDMA is a mechanism that enables data to be transferred from one memory to another memory in a remote system. If we take this system as an example, with RDMA, you are able. The most important here about RDMA is without involving the CPU or the operating system. That's the most important aspect of it, and also using the high-speed network. The example here is that transferring data from a GPU memory to the GPU memory on another node with RDMA, it will go through the network interface card and then the high-speed network without involving the operating system to the network card and then to the GPU, to the memory of the GPU in a remote system. And the particularity of this of RDMA is that it reduces the load on the operating system, unlike other traditional protocols like TCP, where the communication is very slow. Now the question is, because now I mentioned this is a simple example of two compute nodes. Now the question that we can think about is, what about having thousands of compute nodes in a system? How is it possible to each compute node should be able to talk to another 999 compute nodes? So this is one of the challenges with designing a high-speed network architecture, because the design has to maximize the bandwidth and to minimize latency. The communication should be instantaneous, and more importantly is the network should support hundreds of thousands of endpoints without significant degradation of the performance. To be able to connect all these compute nodes to each other, we need a high performance interconnect. In the market, it seems NVIDIA is dominating the business of interconnect for InfiniBand with 64% and 14% by Cray and 13% by Intel. So in the rest of this presentation, we will focus on HPE Slingshot network, simply because our new system will be based on HPE. We'll use HPE Slingshot network. So the HPE Slingshot network consists of basically two components. The Cassini network interface card, I have briefly talked about it, and the next important component is the Rosetta switch. The Rosetta switch comes with 64 physical ports, and this is an important component in combining thousands of compute nodes together. So the role of Rosetta switch is it enables organizing compute node in a very structured way in a network topology, and the network topology, it follows a dragonfly topology. We will come to this term later on. So this is the architecture of the Rosetta switch. It's organized in sort of grid, with here 64 physical ports, is split in terms of row buses. So each the row bus here is used to transfer the corresponding data to other 16 physical ports. And we have the physical crossbar here that guarantees that different type of meters do not get interfered. So in general, when a node wants to send data, it will go through a series of network switches, and the network, it follows a certain topology. So the topology that is adopted by HPE Slingshot is a dragonfly topology. One of the reasons behind it is that the length of the cable becomes to take into consideration the length of the optical cable, which makes the system, reduce the cost of a system. Of course, in addition to the high bandwidth and low latency and scalability. So to understand the role of Rosetta, let's take a simple example here of an example of 72 compute nodes, a system of 72 compute nodes. Dragonfly topology is organized in a group. So in this example, we have 9 groups. So each group has 4 switches, 1, 2, 3, 4, and each switch consists of 2 or can connect to 2. It has 2 physical ports or can connect to 2 compute nodes. In the total, we get 72 endpoint, 9 times 4 times 2. And with this structure, a compute node can communicate with any other compute node in just 3 steps. The technical word used here is 3 hops. Let's take the example. If this compute node want to talk to a node B, for instance. So the way it works is that the node A will send data to the switch. The switch 1 forward the data to the switch number 2. In the same way, the switch number 2 will transfer the data to the switch number 3, and the switch number 3 will deliver the data to the compute node. So this happens at the same group, and the connection is local connection. So the same scenario happens outside the group, and because of that, we build sort of connection between different switches and different groups, and this different connection is what we call a fabric. So a network fabric is a connection between different endpoints. This is a very simple example about building a system of 72 endpoints. This is a more complex scenarios where building a system with 272,000 endpoints. So my idea is, let's see how this number will arrive to this number. As I mentioned, in Dragon topology, it consists of groups. So in this realistic case, or this big system, each group has 32 switches in this case, and each switch has 64 physical ports. Here, not all the physical ports are used to connect to compute nodes. Only 16 ports of each switch are used to connect to compute nodes. The other 31 ports are used to connect switches to each other. And the rest is to connecting groups to each other. So connecting switches, and physical port to connect to compute nodes. So in the total, we get 512 nodes on each group. So each group has 512 nodes, and we have 545 groups. We get a total of 279 endpoints. This is a very complex system. So the complexity of this system, of course, it brings some challenges. So, and one of the challenges here is how to deal with the traffic bottleneck. So the traffic bottleneck here, or the congestion, it happens for many reasons. There are one of the reasons is that multiple packets of data follow the same path, and which causing delays and slowness of the network. But also many packets of data follow the same path, but affecting the bandwidth availability. And also sometimes the bandwidth is not balanced between different physical ports. So all these issues, it leads to slowness and blocks the traffic of the network. But HPA Slingshot comes with some features to overcome those issues. So some of the features is they have a advanced congestion management, that is collection of techniques to prevent, to detect, and prevent a congestion network. And that helps to reduce, and also has an effect of reducing the packet loss and managing the bandwidth between all physical ports. In addition to this advanced congestion management, there is another feature, which is adaptive routine to optimize the network traffic. And another interesting feature of HPA Slingshot is adaptive routine to optimize the network traffic. So what this feature does, it changes the path dynamically of a packet to a less congested path, and that it's the changes is based on some real-time network and queue length. So this feature, it can select the best path for a specific packets. And the last feature here is the quality of service. This is a service that set up the priority, set up policies to prioritize important traffic. So these are some of the features that are integrated into the Slingshot hardware, mostly to optimize the traffic. So beyond these features, of course, there is a need of a software stack that will enable direct communication between different endpoints or different compute nodes by providing a standard API for network communication. So the well-known network communication frameworks here is Live Fabric and Unified Communication X, UCX. So those are the well-known framework for enabling direct communication between different compute nodes. These two libraries, they have basically the same goal. So both they are both collection of libraries to abstract diverse networking technologies, and they enable fast data transfer between different endpoints with a minimal delay. To understand the role of this Live Fabric, we can take let's look at this scenario of two nodes. So sending the data from a process 0 to a process 1 by utilizing the high-speed network wouldn't be possible without Live Fabric or UCX. So this is an important role of this communication framework. Otherwise, it will follow a slow protocol, which is TCP, and the communication will be very slow. So, and another important aspect of these frameworks is they utilize the RDMA capability, remote direct memory access. So which means that the data can be transformed from the memory of the GPU on this node to the memory of the GPU another node, without involving the CPU, without involving the operating system, and by utilizing the high speed network. One important information here is that since talking about lib fabric and UCX, Slingshot 11, for instance, it primarily utilizes lib fabric. And so far, it doesn't support UCX with HPA Cray MPI. So this is an important information to verify whether using lib fabric or UCX. Let me see if we have any questions here before I go to the second part.
Yes, one question if you can take. Does lib fabric also support OmniPath?
Yeah, that's a good question. We will see that we will see it on from the perspective of the lib fabric architecture. And we come to that. We will come to that question. Okay.
Yes, go ahead.
Yeah, I was thinking about the OmniPath. Okay, I mean, OmniPath for UCX, yes, it supports lib lib fabric, but I'm not actually sorry. UCX does support, yes, does have OmniPath, but I'm not sure really about lib fabric. This is something I have to think about, and you can yeah. Thanks for the question. So back to the architecture of the lib fabric. So the lib fabric, the architecture here consists of 4 layers. You have the first layer, which is the user's application, consists of a programming model, for instance, API. We have the lib fabric. This is an abstraction of different API, and the real implementation, it happens really at this level where the abstracted API is translated into structures that is specific to the hardware. And then we have the hardware here. So very briefly, some component here, for instance, within the lib fabric API is the communication. So it stores communication and information about different endpoints. Another important aspect here is the data transfer, that it consists of tag matching option, for instance. So when sending a message, so each message has a tag, and that is avoiding confusion or interference between different messages. And also remote memory access, where a process can access a memory of another process remotely. And we have the atomics option that to prevent any data corruption or rate condition. So you can see here on this is abstract API, and this is here the real implementation. What else? Yeah, so that's briefly about the lib fabric architecture. For the UCX architecture, UCX architecture consists of different layers. We have the top layer. The top layer is user application. So we have a UCP protocol layer, and you have the transport layer. If you look at the protocol layer, it's somehow is similar. The consistent of this layer is somehow similar to the lib fabric, because you have the tag matching, atomic, and remote memory access. So the same functionality. At the low level, this is a high level API. At the low level, it consists of RDMA capability, as I mentioned, that enable memory-to-memory transfer in a remote system without involving the CPU. It supports the GPU accelerator, both CUDA and the ROCm, but also there is a support of other networks, OmniPath, since we talked about, we mentioned OmniPath and Cray. But we have to be careful here about the Cray in terms of support. As I have mentioned, in the previous slide, so Slingshot does not really support. I mean, I'm talking about Slingshot 11 doesn't support UCX so far. So with MPI Cray, probably things will change in the near future. One important message to take here is that when you have a system that supports both libfabric and UCX, so this is it's very important that to benchmark an application on both protocols. This is an example where the benchmarking of fast libfabric versus UCX. What I have noticed here in this comparison is that the performance with the UCX is almost 3 times the performance of libfabric. So I don't think this has to do this comparison. I don't think the low performance notice here, I don't think it has to do with the libfabric, but mostly because the benchmarking different MPI operation does not align with the observation here, meaning that there is something that goes beyond just libfabric versus UCX that needs to be taken into consideration. Yeah, as I mentioned, if a system offers both protocols, it's a good practice to benchmark both to identify which one offers a better performance. Okay. I don't know if we have any question before we go to the parallel file system. Let me see.
No, go ahead. No open question yet.
So after talking about the network architecture, I thought it would be good to give a short introduction to Lustre file system. So Lustre is a file system software platform that is designed for high-performance computing systems, and it's primarily utilized for managing service storage devices and file system. So file system is the structured way of organizing files, sort of in the form of files and folders. And Lustre allows multiple clients, can be login node or compute nodes, to read and write data simultaneously. And another key feature of Lustre is the ability to scale both the storage capacity and the bandwidth independently, meaning that you can add more storage without affecting the bandwidth, and you can increase the bandwidth without affecting the storage. Let's look at the architecture of Lustre, how it looks like. So this is a general architecture of Lustre. It consists of Lustre clients. So Lustre clients can be login node, compute nodes. And we have a metadata server that manages the access to the metadata storage, and also handle metadata operation like creating a file, deleting files. So, and we have the metadata storage here, where the metadata information such as directories, file name, permission, and so on, they are stored in the metadata storage. And on the other hand, we have, and the actual data is stored in the object storage, and the object storage is managed by the object storage server. And the system here can contain many object server, many object storage server, and many object storage targets. Yeah, so this is an overview of different components of the architecture of Lustre. I want to summarize here some Lustre capability. So one of the features of Lustre is it can support a file system up to 512 terabyte and a single file of up to 32 petabytes. Lustre also comes with a high throughput up to 2 terabytes per second in production system, and it can support up to 10 million files in one directory and up to 2 billion files in the file system. Another interesting aspect of Lustre is also it supports up to 25 clients login node compute nodes. Since we talk about Lustre, I want to give an example here about the storage system on Lumi which uses Lustre. So the storage system here consists of two partitions. There is the main partition, which has the capacity of 20 petabytes of data with a theoretical bandwidth of 240 gigabytes per second. And it consists of one metadata server and 32 object storage, and the storage type is HDD. Another partition is flash storage. It comes with the capacity of 8 petabytes, the speed of bandwidth of 1.7 terabytes per second. It has two metadata server and 58 object storage, and the storage type is SSD. So you can basically get this information by just running this simple command to get a summary of different type of file system. Yeah, I think since we are running out of time, I will skip this part and go directly to the conclusion.
Can you give us a short summary of the part you are skipping, Hicham?
Yeah, so there are some new features that could be implemented, and it enhances the performance. One of the features here is the GPU aware MPI. And the GPU aware MPI is basically the arguments that are the device pointer are basically passed as an argument to an MPI routine. And in this case, instead of process 0 talk to process 1, the system will behave like GPU 0 will talk to a GPU 1. And the concept of MPI with GPU awareness is based on a concept called unified virtual addressing, in which you have a single virtual system that combines the system memory and the GPU memory. And so the way it works, instead in traditional way, when the aware is disabled, where the communication takes a long path, which is the case here, it will take a very short path, enabling transferring data between the memory of the GPU 0, for instance, and the memory the memory of the GPU 1. Instead of going from the memory to from the GPU memory to the CPU memory, and then to the CPU memory, and then to the other CPU, and from then to the other GPU memory, which is a very long path. It increases latency. So this is one of the particularity of GPU aware features. But also in multiple node, it's also possible to make use of RDMA capability that we mentioned. And by using this capability, what happened is that communicating between two nodes with the user RDMA, the data will be transferred from the GPU memory to the network card, and from the network card through the high-speed network to another network card, and from the network card directly to the GPU memory. That's called GPU direct RDMA, instead of traditional way where there are additional overhead, which that increases latency.
Mm-hmm.
This is an example where we can see the benefit of introducing this feature. The first thing is that if the communication involves a small set of data, you barely can see any performance. But once you increase the size of the data, for instance, here for 1 giga, so you can see that the switches enhances the performance by a factor of 13 by enabling these features. So just to conclude, I have talked about architecture of different components of the hardware, from the compute node to the CPU to the GPU. And understanding this architecture, it helps really optimizing the application by taking advantage of some options like CPU affinity, Newman node, memory hierarchy. We talked about the network fabric architecture. So it gives an idea about how a system is built, how servers they are connected to each other, but also it gives an idea about some features like RDMA capability, how it works. We also talked about leaf fabric and use case briefly, and we mentioned that if a system offers both protocols, so it's wise to benchmark both protocols to help getting better performance. And also we talked briefly about Lustre architecture and as a management as a software platform to manage software devices and file system. And one of the capability of Lustre is that it scales up to more than 25,000 clients with the capacity of 512 terabytes of storage. So some general comments here. In general, we associate the word idle to computation on either CPU or GPU, but also the idle can be associated also to the network. So to take advantage of both of the fast network, it would be good to overlap communication and computation. For instance, on the CPU, when using API, it's good to use non-blocking communication, and on the GPU, asynchronous programming via streams. And as there is development of new hardware features, it requires also from the user to utilize those features to enhance the performance. And yeah, last but not least, the high-speed network, or in general HP system are designed to handle large amount of data, meaning that once the communication involves small set of data, the system basically struggle and barely you can see any performance. So I think I will stop here if there are any questions.
Thank you so much, Hicham. You covered a lot. It's not an easy task to cover this much topic in 1 hour, but it was very concise and well informed. Thank you so much for your work here on the talk. I hope all of the participants enjoyed this talk. If you have any question, please use the Q&A. We answered something on live, but if we can still take a couple of questions. Thank you then.